So this is section 6.1.3, connecting the unit circle to triangles and looking at the law of sines. We just finished looking at that map and that Lake Margaret problem and discovering that there is actually two maps, and we had to find the hidden solution. So the same case is going to happen when you're looking at triangle problems like this. You're going to have to outsmart the calculator and figure out where that hidden solution is. So we're going to call this the ambiguous case of the law of sines. Specifically, this will deal with ASS, or this is the case of the donkey. This is the only situation it happens in. The other congruence postulates, side, 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 it never happens, but this is one of the reasons why it's an outcast. Alright, so if we're looking at this, before we get into the actual problem, it will be helpful to kind of set up a table where we can determine whether or not there is one triangle or two. So I'm going to use pictures to illustrate that. So if A is less than B, and the other scenario is if A is greater than B. Alright, so say we have an angle side-side triangle that looks something like this. I'll give you some measurements. So this is angle A, side B, side A. And you know this angle is fixed. So you have your angle side-side. Now, you can rotate this angle right here. You can rotate it this way because it's not fixed at the moment. So when we rotate it, because angle or side A is shorter than side B, if we rotate it just enough, it's going to come back and it's going to swing around and end right probably around there. Which means we actually have a second triangle that fits the same criteria. Angle A is still the same, side B stays the same, and side A stays the same. It's just been swung over. So you see from this drawing, when the opposite side is shorter than the adjacent, you have two triangles. Now, it really helps to see the other triangle drawn out, because then you're able to compare and see why this one doesn't work. So same scenario, except one thing changes. Now side B is shorter than side A. Side A is longer. And again, we're going to swing this side. And you'll notice if we swing it, A is too long. It's going to actually swing all the way down here. You can kind of see it rotating here. It's going to overshoot it. So in this case, when side A is longer, or the opposite side is longer, you're only going to have one triangle. And you will have to determine that to know how you're going to solve. Alright, so after you have your two triangles in mind, you kind of have to determine whether or not the problem you're working on is going to have two or is it going to have one. So we're going to find the missing sides and angles. And we'll build this triangle for you. Let's see. So I'll give you some dimensions. This is going to be 6, and this will be 7, and we're going to make this 30 degrees. Now, remember, this is the leg. This is what you can pivot. So if we rotate the smallest side, you can see that there will be another triangle that ends up right about here. We have two triangles. So that allows us to have a framework for solving. Now we have to find that hidden angle. Alright, so we have two triangles. Now we can use the law of sines to set this up. Sine of 30 over 6 equals sine of blank, we'll call this angle B, over 7. We get 7 sine of 30, equals 6 sine of B. It's important not to put this in your calculator until the last move, so we keep it accurate. Divide by 6. Now, if we do that, we end up getting I should use my calculator here. Let's see, mode, 1 degree, 7 sine of 30 divided by 6. You get 0.583 equals sine of b. That I do want you to put in your calculator. Now leave that number in there. And now I have to get rid of the sine. We take sine inverse. This is the crucial move. Sine inverse, these cancel. And you're left with angle B. Do second sine of the answer. You get angle B approximately equals 35. Now here's where we can round, 35.7 degrees. Alright, so that gives us angle B. Now, we need to connect this to the unit circle. What this is saying on the unit circle, sine is your y coordinate. Where is your y coordinate? 0.58. You have two places. 0.58 is about here and about here, because this is 0, 1. So that's a height of 0.58. 35.7 is in quadrant 1. But there's another angle. It's this one. And to figure it out, we need to go backwards. So we're going to take 180 minus 35.7. Let's see what we get. I think we get 144.3. So then this angle here is 144.3. This is our hidden angle. Alright? You will always, so for this triangle, since we have two triangles, we need to determine that second angle, which is subtracting from 180, which you'll always do to find it. Find that missing angle. So we can write this in. This is 35.7. Now it's going to be helpful to draw in your second triangle. So I'm going to draw it so you can see it. Still 7. This is still 30. But now we have this piece, which is 6. So we've rotated it. 6. This is 30. And then now, instead of this angle being 35.7, it's 144.3 from the subtracting from 180. So this is kind of the crucial part of the problem, being able to identify that there's two angles that add up to 180 when you take that sine inverse. So here's kind of the big move, sine inverse. To solve for the rest, you're going to use law of sines. I'll give you the answers for this. I think you find out that this angle here is 5.7 degrees, and then this side is 1.2. You do that, find that using the law of sines. And this angle is 114.3 degrees, and the opposite side is 10.9. Which triangle is correct? Both of them are correct, because you have two triangles in this. Now, if we determine at the beginning that there's only one triangle, only the first one would be right, you would not have to do the inverse. Remember the crucial step, kind of right here, taking that sine, taking the sine inverse of that angle, finding the hidden angle, which is 144.3. Alright, you will see this problem again, I promise. Determine whether or not one or two triangles, and then solve using the law of sines.